What if we could build a replica of the sun on Earth? For centuries, humanity has gazed up at the sun and marveled at its seemingly boundless power, a blazing sphere of plasma, incandescent and eternal, at the heart of our solar system. The sun sustains all life on Earth, its energy warming our planet, driving the weather, and fueling the growth of plants. But what if we could bring even a fraction of that cosmic furnace down to Earth? What if we could build a replica of the sun right here, on our own world? The prospect is a tantalizing one, at once daunting and full of promise. To truly grasp what it would mean to recreate a piece of the sun on Earth, we must first understand what the sun actually is, not just a bright disk in the sky, but a churning, dynamic engine of energy, governed by the most fundamental laws of physics. The sun is a massive ball of gas, mostly hydrogen and helium, held together by its own gravity. Deep in its core, immense pressure and temperature force hydrogen atoms together, fusing them into helium and releasing vast quantities of energy as radiation. This process, nuclear fusion, is the wellspring of the sun's luminosity and longevity. On our technologically evolving planet, the dream of capturing fusion's promise has captivated researchers for decades. Could we unlock the secret of the stars and use that knowledge to solve some of humanity's most pressing problems? In laboratories around the world, teams of scientists have come ever closer to creating a controlled, miniature version of the sun, a feat that, if achieved, could revolutionize the course of human civilization. But what would it take? What challenges would we face? And what new world might we awaken if we succeeded? Let us first imagine, in vivid detail, what it would mean to build a replica of the sun. The sun itself is enormous, more than 100 times the diameter of Earth, with a mass 330,000 times greater, and an internal temperature at its core reaching an astonishing 15 million degrees Celsius. Of course, building a replica at the sun's physical scale is not feasible. After all, the sun is nearly 1 million Earths in volume. Instead, we imagine a scaled-down version, a star in a laboratory, not one that could outshine our sun, but one that could safely deliver usable energy to our world. To recreate the sun's core, we would need to generate and confine plasma, a state of matter where electrons are stripped from atoms, creating a soup of charged particles at temperatures hotter than any found naturally on Earth. This plasma must be squeezed tightly enough and kept hot for long enough for nuclear fusion to occur. Hydrogen nuclei, or isotopes, like deuterium and tritium, combine to form helium, releasing energy according to Einstein's famous equation, EXMC2. But unlike the sun, which uses the immense force of gravity to achieve these conditions, we would need to employ ingenious technological solutions to replicate the necessary temperature and pressure. This is the fundamental challenge of fusion research: how to imitate a star using human-made devices, constrained by the limits of terrestrial materials, safety concerns, and engineering budgets. Let's journey through the heart of these efforts, to magnetic confinement, inertial confinement, and the dizzying array of approaches humanity has taken in our quest to bottle a star. The best-known design, and the one that has reached closest to break-even, is the magnetic confinement device known as the tokamak. This works by generating a powerful magnetic field that twists into a toroidal or donut-like shape, confining a seething plasma of hydrogen isotopes. The plasma inside the tokamak is incredibly hot. Temperatures necessary for fusion are on the order of 100 million degrees Celsius, several times hotter than the sun's core. Since at the lower pressure available on Earth, we need more heat to compensate for the lack of gravitational compression. Other approaches, such as laser-driven inertial confinement, use banks of powerful lasers or particle beams to compress tiny pellets of fuel in a rapid, miniature implosion. For a fleeting instant, conditions inside the fuel pellet imitate that of the sun's heart, unleashing fusion's signature burst of energy. Each method pushes at the boundary of the possible, wrestling with the twin problems of sustaining the high temperature and compressing the plasma without melting or destroying the apparatus itself. Suppose, after decades of research and effort, humanity finally achieves the dream. Construction is completed on a monumental fusion facility, and for the first time, it powers up. A sun, in miniature, is born on Earth. The reactor roars to life, invisible magnetic fields taming a violin-bright ring of plasma. Or perhaps, a sequence of laser shots creates hundreds, even thousands, of tiny artificial stars each day. For the first time, humanity wields a controlled, inexhaustible source of energy, clean and essentially limitless. What changes, both for us and for our planet? The implications are staggeringly profound. Energy, ever since the dawn of civilization, has been the lifeblood of technological progress. From fire and muscle, to steam and oil, to the electric grids of today, our societies have advanced as we have learned to capture, store, and harness ever greater amounts of usable energy. But every energy source has brought with it both benefit and risk. The pollution of fossil fuels, the dangers of nuclear waste, the intermittency of renewables. Fusion, unlike fission, produces almost no long-term radioactive waste. Its fuel, hydrogen, is the most abundant element in the universe and can be extracted from seawater. The process, properly designed, cannot create the kind of runaway chain reaction that makes fission dangerous. It produces no carbon emissions, no air pollution, and carries minimal environmental risk. If we could build a fusion-powered world, energy scarcity would fade into the past. The price of electricity would plummet, opening the door to innovations barely dreamt of. Imagine a planet powered by tabletop suns. Massive desalination plants transform seawater into endless supplies of fresh drinking water. Electricity-hungry industries can operate with a clear conscience, knowing that their energy is sustainable and clean. Electric vehicles recharge in seconds, freeing nations from the clutches of oil and the geopolitics of fossil fuel. Entire megacities spring to life, their lights and factories humming with energy drawn from the heart of a star. Perhaps most importantly, a fusion breakthrough would fundamentally alter the trajectory of climate change. As humanity's appetite for energy grows, carbon emissions have driven the world toward global warming, threatening ecosystems, food supplies, and the habitability of our coasts and cities. If fusion power could cheaply replace coal, oil, and gas, the reduction in greenhouse gases would be unprecedented. The air would clear, seas would stop rising, and the world could focus on healing the wounds left by our fossil-fueled past. But the dream would not end at the borders of Earth. With fusion as our torch, humanity could take its place among the stars. Rockets powered by compact fusion drives could reach the outer planets and beyond, untethered from the need to carry vast stores of chemical propellant. Long-term bases on the Moon or Mars could flourish, their power needs supplied by self-sustaining fusion reactors. Asteroid mining, space habitats, and deep space exploration, all would be within our grasp. There is, however, a shadow side to this dawn. History teaches us that new technologies, even those born of hope, can carry risks and unintended consequences. The knowledge required to build and sustain a star on Earth is immense. The engineering challenges, while not beyond imagination, would require unprecedented cooperation, investment, and attention to safety. Even a small, controlled star is incredibly dangerous if mishandled. An uncontrolled release of energy could devastate a facility or its surroundings, though not on the scale of a nuclear fission reactor. There are also the social and economic consequences to consider. An energy revolution of this scale would disrupt old industries and national economies built on fossil fuel extraction and export. Entire regions of the world, once wealthy from oil or coal, might struggle to adapt. Millions of jobs would change or vanish, demanding proactive reskilling and investment in new opportunities. The transition to a fusion-powered world could be as turbulent as it is transformative, and yet the benefits would far outweigh the risks. Science tells us that most problems in the world, from hunger to poverty to disease, are in some way linked to energy. Its cost, its availability, its source. Clean, copious, and cheap power would empower every corner of the globe to rise, lighting villages, purifying water, driving industry, cooling homes. Wars over oil and gas could become relics of the past. Let us pause and also contemplate the sense of awe. the symbolic import of this achievement. For all of human history, the sun has stood as the ultimate source of mystery and power, a thing to be revered, feared, and worshipped. If, through reason, creativity, and perseverance, we succeed in mirroring its fires in our own world, it would mark a new epoch in the story of our species. No longer passive recipients of solar warmth, but active weavers of starfire. Our civilization, once vulnerable to cold and dark, would at last command the flame that drives the heavens, yet such a world could only arise from years, decades even, of sustained effort. Fusion power is often described as always 30 years away, a testament to its difficulty and elusiveness. The obstacles are not trivial. The materials required to build and maintain a fusion reactor must withstand immense heat, neutron bombardment, and electromagnetic stress. The fueling process, particularly with isotopes like tritium, is technically challenging since tritium is radioactive and must be bred within the reactor itself. And the cost, billions of dollars per facility, demands societal will and government investment. But the roadmap is clear, and the pace of progress is accelerating. Experimental machines such as ITER in France, the largest and most ambitious tokamak yet constructed, are aimed at demonstrating for the first time that fusion can produce more energy than it consumes, a feat known as ignition. Private startups, nimble and innovative, race to invent new reactor concepts, pursuing alternative fuels, reactor designs, or even fusion powered by advanced lasers or magnetic fields. Each success brings us closer. More efficient magnets, longer plasma confinement, better superconducting materials. Suppose we reach the turning point, a world where fusion is cheaper, safer, and more reliable than any other form of energy. What would change in our daily lives? The price of electricity, for one, would reach new lows, accelerating technological innovation around the world. Entire industries, from transport to computing, could electrify, no longer constrained by the cost or carbon footprint of their power. Electric aircraft, previously impractical, could soar between cities. Data centers, hungry for power, could expand without limit. More profoundly, the very choices we make about our societies could shift. Reliable, sustainable energy is the foundation for prosperity. Healthcare, education, communication all depend on ready access to power. In the developing world, rural electrification would leap forward. New opportunities would emerge in agriculture, industry, and information. On a more speculative note, fusion might even reawaken our commitment to tackling the greatest challenges of the future: terraforming deserts, reversing the course of environmental damage, fostering cities that balance human life with the rhythms of nature. With energy constraints removed, innovation could move from the zero sum to the positive sum, from competition for scarce fuel to cooperation in the service of all. Let us also not forget the scientific boon. A replica of the sun on Earth would serve as the ultimate testbed for questions at the frontiers of physics: plasma turbulence, magnetic reconnection, particle acceleration, even perhaps new states of matter. Our understanding of the universe, from the workings of distant stars to the fate of galaxies, would grow richer with each new experiment and discovery. But what about the risks? With star power in our hands, new forms of regulation, oversight, and international cooperation would be necessary. The immense power at stake would require transparent safety systems, robust risk assessments, and above all, a culture of humility, recognizing that even the brightest flames can burn. International coalitions would be needed both to fund and to govern these new suns, ensuring that their benefits are spread widely rather than hoarded by the wealthy or powerful. And yet, the greatest risk may simply be in not trying. As humanity stands on the cusp of the 21st century's challenges, overpopulation, resource depletion, climate change, the old answers will not suffice. Fire was the start. Starfire, perhaps, is our destiny. The dream of building a sun on Earth is a symbol, a call to action, and a reminder of all the latent promise within our species. From a certain point of view, we already live in the light of a star. The sun's photons, warmed by fusion, flood our world every second of every day. Solar panels, wind turbines, even the food we eat and the fossil fuels we burn are down payments on that primeval fusion. Yet to command and control that celestial fire, to ignite it when we wish, to wield it as we will, would be a new birth. The first fusion reactor, bright as a small sun, would mark a new age in science, in technology, and in the story of humanity. Its light, shining from deep within the reactor core, would be the beacon of a civilization that had at last mastered nature, not to dominate or destroy, but to create and to sustain. It would be the fire of hope, a flame to light the centuries to come. In the end, the question is not merely, what if we could build a replica of the sun? The deeper question is this: what kind of world might we build once we finally hold the stars in our hands? The answer lies as much in our vision and responsibility as in our ingenuity. With each step toward fusion, we edge closer to a tomorrow in which energy is no longer a limit to possibility, but a door to discovery. The work is difficult, the risks real, but the rewards, a world transformed, a universe beckoning, are surely worth the burning dream.